Okay. So let's begin again. So what are we going to talk about today? So there's 3 things on our agenda. Maybe I'll attack them in this order because I didn't get to Discord trees last time. We'll do Discord trees first, and then we'll do a little bit about AVL trees, and maybe we'll do a little bit of, I'll come up with a list of exam topics, right, for the first exam, and maybe I'll even go over, actually that's a good question. Do I have my old, let's see if I have them. If I can pull them up really fast, then I'll tell you, and then if I have them, then we can even just look. Yeah, I have the exam that I gave in class from, not entirely sure when, I guess. And then here's the one I gave in the fall of 20. Okay. And let's see here. Okay, so I have the 2 exams. I'll probably release them on Blackboard or Discord or whatever. Okay, cool. So we'll go over some old exams. All right. So I think the first thing to talk about is what is a Discord tree, right? Because as it turns out, Discord trees are an invented thing, right? An invented thing, but it's weight balanced. So basically, let's talk about AVL trees for just half a second. So what is an AVL tree? An AVL tree, right, is a binary search tree, which is height balanced, right? Not weight balanced. And so you might be asking, okay, so I know what height is. Height is the distance, or really height is that formula, right? Height is, the height of a node is 1 plus the maximum of the height of the left node, I guess node dot left, and the height of node dot right. So that is the definition of height. And so height is basically the distance from the, I guess I should say it this way, it's the max distance from a node to a leaf, right? Or something like that, right? Maybe plus or minus 1, depending on how many corrections you have to do. So, okay. So that's what an AVL tree is. An AVL tree is balanced because we require that the height of the node dot left minus the height of the node dot right, and this is kind of pseudo-code-ish, the absolute value, right, of that has to be less than or equal to 1. So that's the AVL rule. Okay. And so, cool. Well, notice that this is all talking about heights. So the question we should ask is, what is a weight? Right? Weight is the number of nodes in a subtree. Right? So that's the difference between height and weight. Weight is how many nodes are in the subtree. And so that, in an AVL tree, the height and the weight are related. But what you actually work on, what you actually try to control, is always the height. You never explicitly try to control the weight of the tree. And so, now, we are going to do a Discord tree, right? So a Discord tree is not a height control tree, it's a weight control tree. So let's look at the rule for this Discord tree and try to figure it out. So here's the important part in the project description, right? Here it is. Where is it? Right here. For a Discord binary search tree, we can define an imbalance to occur when one child's size is 50% larger than the other child, and at least one child's size is 4 or greater. Okay, so really what we're saying here is when the what do we mean by the child size? We mean the child's weight, right? And that's what we mean. And so there we go. And so then larger than the other child and at least one child size is 4 or greater. So what that means is that if we have, I think they're, oh god. Yeah, okay, so let's draw out some examples. Okay. Now, is this just a binary search tree? How did he get, I know he got this visualization from the visualization website, but I'm not sure that there's actually a weight balanced tree there. So I think basically he just put this in as a BST. But let's look at it this way. So so the rule is that an imbalance occurs when 1, the node dot left is bigger than or equal to 1.5 times the weight, I'll call it WT for weight, of node dot right, right? The weight of the node dot left is bigger than or equal to that. Otherwise, the weight of the node dot right is bigger than or equal to, I guess I should call this 1A, and this should be 1B. So one of these has to be true. I'm trying to think if there's some cutesy way that we can avoid doing both equations, but I'm not 100% sure that we can. I think, you know, you'll just have to do 2 cases in that case. So, and the other thing is, and 2 is when the weight of the node dot left is bigger than or equal to 4, or the weight of the node dot right is bigger than or equal to 4. So these are the 2 rules for the tree, okay? And basically weight is always counting the number, weight of a node is equal to the number of nodes in the subtree. Hard to say, but I think probably including the node itself. So the weight of a node, the weight of a leaf is equal to 1, I would think. Let's check and see if he actually tells us any of these weights here. No. Okay, so I'm going to say it though. I'm just going to say it for our condition that oh, I guess here he could say an imbalance has occurred at node 7 since the right subtree is 50% larger than the left, and one of them is bigger than or equal to 4. Well, since both are 4 or greater, and there's only a 2-node difference, but as the size increases, the imbalance will become more apparent. Okay. Rotations would be inefficient. That's not exactly true, but okay. I would have, you know, honestly, I would just delete this whole sentence. Because it's not exactly right. And then, anyway, so instead we can use a sorted array to rebuild the subtree into a perfectly balanced subtree. So, this is how we do it. So first we must create an array and move the subtree's node, to move the subtree's nodes into. So what are we doing here? Basically what we're doing, there's a way to get a list of things. Let's say that you know that there are, I guess, 11 nodes here? So there's 11 nodes. Oh, I guess he actually isn't including this node in the weight calculations of the subtrees, because if you notice, this one is 6, this one is 4, and he's saying that it's exactly 50% larger, so he's not including the node itself in the weight calculation. So I guess the weight of these subtrees would be, well, I guess we're actually talking about the weight of the left and the weight of the right, so he is including the weight of this node in its subtree and the weight of this node in its subtree, so, okay. But the important thing here is there is a way to go through a tree, right? And we talked about it maybe 1 or 2 classes ago. There's a way to go through a tree and to make a list out of that tree. So for instance, if I know that there's 4 things here, and I know that there's 6 things here, then there's 4 plus 6 plus 1 things total in this whole subtree, right? There's 4 plus 6 plus 1. So how many things are in the total subtree, right? There are 1 plus the weight of the node dot left plus the weight of the node dot right. I guess that's actually the weight of the node, right? There's that many things in the subtree. So let's redraw some kind of thing, and let me just show you an example of something. So here, and let's get rid of colors, because colors, there's no color here. There we go. Let's just make some circles. Something like this. I think this is basically what they had in the other diagram, which is, it doesn't really matter if it's exactly what they have in the other diagram, right? It's okay. Because the point is that we are going to, fill it with our own data. And then here, let's just make it even more egregious. Let's put another one of these down here. So here's an example, and it's not exactly the example from the last thing, but it's a new example. It's different. So now we're gonna have, say, let's put pick a number between, let's say 15. Let's say this is 8, 12, 4, and 7. So that makes it a binary search tree. And then here we're going to have, say, 31. This will be 45. This will be 25, 24, whatever. Has to be between these two since it's the right child of the left child. So what is bigger than 24 and less than 38? Let's say 27. And then this has to be bigger than that, so 28. And this one has to be in the middle, so let's say 25. Okay. So, as I have been hinting at, as I've been saying, right, there is a way to do this. There is a way to read out all of the things. So basically, every node in your Discord tree is going to have to keep track of its weight. And the reason why you're going to have to keep track of the weight is because a node itself cannot, unless you do a full traversal, a node isn't going to know, I guess I should say this, just like in the AVL tree, just like in the AVL tree, you need to track the height at every node. In the Discord tree, you need to track the weight. And so that's kind of the point here. So you need to track the weight of the Discord tree at every node. And so you'll need, in your data structure, right? So I'm sure that this is actually in the, let's just check and make sure that this is actually already in the project. I think it probably is. Now, where did I stick the project? There I did. Okay. Let us unzoom. Let us go to discordtree.h. Let us look here. So here we have all of this garbage. Account, which we don't care about right now. D node. My guess is that this is the Discord tree node. Public D node. Okay. Interesting. Not 100% sure what so the account is going to be the data element that we store, right? So that's going to be our value. We have left and right pointers. We have num vacant, which I am not 100% sure what that is. We should read the project description more. Okay. So I guess you can remove an account or something, maybe. And so instead of deleting the account from the tree, okay. This removes a node from the tree. Contrary to the function's name, it should not actually remove a node. Ha! See, as I was saying. So I love these two sentences. This function removes a node from a tree. No, it doesn't. Contrary to the function's name, it should not actually remove a node, but mark it as vacant by setting the dnode's variable vacant to true and increasing num vacant by 1. The node must retain the original discriminator in order for tree traversals to function. The size left-right pointer should remain intact, right? So you do not delete the node. You do not delete the node. You only remove the data from the node. So no. Right? Instead of removing the node and shifting the children up the tree to take the blah, 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 all you do is you mark the node vacant, and you have to keep the account there so that you can still search through the tree, right? It's just marked as vacant. Okay, that's how it is. If you want to implement the functionality recursively to facilitate a recursive implementation, you can introduce the helper function. Okay, I agree. So, yeah, so basically when we are not actually doing tree deletion here, okay? So you know how in order to delete from a binary search tree, you always have to look for the successor node, and then if that successor node is a leaf, you move the value up, and then you delete. That is true. That is all true. This does not remove a node. This removes, it's sort of, right? Okay. Okay, so this function inserts an object into the correct spot of the tree using the traversal rules for a BST. I agree. The discriminator value should be used as a key, and the recursive implementation is recommended, of course. Yep. So to facilitate a recursive implementation, you can introduce a helper function. Yep. So after an insertion, the function should update the sizes and the number of vacant nodes. So what that means is that as you leave the recursion at every level, you should update the size of the subtrees. Especially because once you've inserted, the size of that tree is going to grow, and then the size of its parent is going to grow, and then the size of its parent is going to grow, etc. So you need to update on the way back up. If a node has a discriminator that matches 1 to be inserted, a new node should not be created, blah, blah, blah. So that's just don't make duplicates. If a vacant node is encountered, oh god. So if a vacant node is encountered, the account can be placed in that vacant node if 2 conditions are met, if the binary search tree properties will be maintained. So what does that mean? What does that mean, right? That's actually hard, right? That's hard. And let me show you why that's hard. And then let's read the second one. So the discriminator isn't already in the tree. Okay, so this is hard, I think. If I'm not crazy, this is moderately difficult. And here's why I think it's moderately difficult. Let's make a copy of this tree here. Okay. So if we look at this tree, and say I delete this one, so now this is vacant. So this is vacant. True. But the secret value, right, is equal to 15. So, okay, so we still know how to search through this tree, because if you come down, like if this is not the top of the tree, if this is just one node, then you get down to here and you know which way to go, right? If you're less than 15, you go to the left. If you're bigger than 15, to go to the right. But let's say that you're inserting 16, right? Let's say you're inserting even, say, 17 or, say, 20, right? Let's say we're inserting 20, and then let's also insert, for instance, 29, right? 29, for instance, right? Okay. So here is the problem. It is possible, if this is vacant, you can insert this node here, and this can become 20. So this works, right? And so you might ask, well, why do I know it works? Right? So this works. And the reason why it works is because if you look through this tree and you say, is everything here less than 20? The answer is yes. And the reason why everything here is less than 20 is because the value is 15, so everything in here has to be less than 15. So this side is good, right? Everything over here is good. We're happy over here. Happy. Because 15 is less than 20. But what about this side? This side, it works too. But why? And the answer is, it's not because 20 is less than 31. Certainly not. Right? It's actually because 20 is less than 24, which is equal to the min thing in the right subtree. Now, there is a name, actually. There is a specific name for the smallest element in the right subtree, right? Because, and what is that name? Right? What is the name of that thing? So the hint is that we have to find it when we do the deletion, right? It is the successor object. So the reason that you can insert this thing here is because the successor of the node is less than 20, right? If the successor of this node were say instead of being 24, this was I guess 18, right? So it was 24, 24. Now it's 18, right? Then it doesn't work anymore, right? Because you can't insert. You can't put 20 here, because if you put 20 here, then basically what happened is you have to pretend that when you inserted 18, it went in the right direction, but you see 18 went in the wrong direction now, right? 18 should have been on this side and not this side. So that's why that requirement, even though very little is said about that requirement, right? The BST order property will be maintained. That is a very difficult part. That is probably the difficult thing to do. And the way that you have to do it, the thinking that you have to do for it is, if you're going to insert a new value that is bigger than the previous value in that vacant node, you have to check the successor node, right? If the successor value is bigger than whatever you're going to insert, you're good. Okay, and that's if you're going to insert to the right. Does that make sense? Or I'm sorry, if you're inserting, I'm sorry. What I meant by that is if you're inserting a new value that's bigger than the previous value. Because if you're inserting a new value that's bigger than the previous value, then you are going to be okay on the left side, but you might have a violation on the right side. And so that's why, as I said, with 29, 29 does not work. Because even though 29 is bigger than 15, so all of the stuff is less than that, so if you put it in here, it'd be okay on the left side, it's not okay on the right side. Even though it's bigger than, even though it's less than 31 and less than 45, so it's okay here. The problem is that if this is 18 or 24, it doesn't matter. It's still, this node causes a problem, right? This node causes a problem. Because, so do all of these nodes too, but really this one is the problem. Because this node here is the successor node, right? That's the successor node that causes the problem. So, okay. So that's the point, is that, you know, this is the node that you have to check if you're going to insert a node that's bigger. And of course you might ask, well, what if we need to insert a node that is smaller? And it's almost the identical answer. And of course I never actually taught you this word, in terms of trees, but you can imagine that the word that we're looking for is, instead of checking the successor node, you check the predecessor node. And of course you might ask, 25, so the thing is that 25 doesn't matter. And the reason why 25 doesn't matter is because everything to the right here, right? Everything to the RIGHT of 24 is going to be bigger than it. So it's also true, you're right, you're correct, that 29 doesn't work because 24 doesn't work, but it's also true that it doesn't work because 25, 28, 27. But if there were some extra nodes here, like say we had even more nodes on this subtree over here, let's say that we went down like this, and then down like this, and then maybe like this, and so we had, 23, 22, 21. So now the predecessor node is not this node, right? Now the predecessor node is this node. And remember, the way to get to the predecessor is you always go to the right one step, right? It's actually an interesting thing to get the successor node. It's basically equal to right once and then left as many times as you can, right? So that's how you get to the predecessor node. So even if there's like a bunch of stuff in all of these other subtrees, that's exactly correct. Or so predecessor is the opposite of that. So the successor, I should say, I think I might have accidentally said predecessor with this, but what I mean is the successor on the right side is right once and then left as many times as you can. The predecessor node, is left once and then right as many times as you can. And what does that mean? What that means is, so, I mean, obviously here, the predecessor node is this one, right? That's the predecessor node. Let's make it, I don't know, purple, whatever. So the point isn't what the color is, right? The point is that this is the predecessor, this is the successor, and that's it, right? And this is the predecessor. I'll just call it pred. So you're 99% there. So basically the successor is the smallest node on the right side of the tree. So it's the, I guess you call it like the minimum, right? The minimum node on the right side. And the predecessor is the max node on the left side of the tree, right? And so that's exactly how you compute these things. And so that's how you're going to have to determine if it's okay. So let's say that the secret value is 15, right? And so you know that 20 will work because 20 still works because 20 is still between the predecessor and the successor. So if you picked a value, if you tried to insert, say, 14, right, or 13, as it turns out, 13 works, right? But 13 doesn't work for the same reason that 20 worked, because 13 is less than 15. So 13 would have been inserted on this side of the tree, and so what you have to do is you have to find the predecessor, and then you ask, is 13 bigger than the predecessor? So the rule is that either you have to be bigger than the predecessor and less than, I shouldn't say either. You must be both bigger than the predecessor and smaller than the successor. But notice you only have to check one. And the reason why you only have to check one given any value is that if the node is smaller than the secret value that used to occupy this position, then the point is, if the node is smaller than the previous value, the vacant value, then the point is that it's definitely going to be smaller than the successor, because the successor was inserted to the right even with a bigger value, right? So, and the same thing is true. If the node is bigger than the previous vacant value, then it's going to be bigger than the predecessor. And the reason why that's true is because the predecessor was inserted to the left with a bigger, with a smaller value, right? And so you only ever have to check one side, but you do have to check one of those sides. So that is what it is, and then that's how you have to. So this is, as I say, I do like how it gets like a single line here, but right, but yeah. So this definitely requires some thinking. So you're probably gonna have to even think kind of harder. That, I mean, this is just like the picture proof kind of stuff. You're gonna have to actually think about how to make this into code, and you know, I'm not promising it's gonna be easy, but at least now I hope you have some understanding after you listen to this of how the insert into the tree works. And then of course here, I wonder, when are you supposed to rebalance? So I think, let's see. After an insertion, the function should also update the sizes and number of vacant nodes, as well as check for an imbalance at each node. So it's basically the same as an AVL tree. We're going to check for an imbalance at every stage of the insertion. And then if the node has a discriminator that matches the one to be inserted, okay, no, this is just don't insert duplicates. Okay. And this is when you can put in a vacant. So let's go and talk more about the balancing operation on a discord tree, right? So what does the balancing operation look like on a discord tree? And so let's just stick, let's steal this tree, right? Steal the tree, except instead of putting in 15 there, we'll just stick 13 on there, and everything is fine, right? So here we don't. It doesn't really matter. We don't have any vacant nodes. Nothing matters. But let's say that we've just inserted 21 into this tree, right? Pretend we've inserted 21. Okay? So if we've inserted 21, and this is the tree that we have, now of course I don't think you can actually get to this tree with the discord tree, because I think it will have rebalanced by this point already. So again, I don't think you can actually do this, but let's say that this is something that we want to discord balance, right? So let's think about how this is going to work. So basically here, we look at this and we say, okay, the weight of the left child and the weight of the right child are both 0 here. The weight of the left child is 1. The weight of the weight of the right child is 0. So no rebalancing. Remember that the rule is that we need one of the weights. One of the weights must be bigger than 4, or bigger than or equal to 4. So okay, if that's true, right? If one of the weights must be bigger than or equal to 4, then it's not going to be here. The weight here, the left weight is 2, the right weight is 0. The left weight here is 3, the right weight here is 3. So actually, notice what this is doing. So, you know, this might be offensive to us as a kind of AVL tree type balance, right? But this is why weight balancing, this is where weight balancing is a bit odd. And the reason why is because it doesn't detect different shaped, different height subtrees. And so you notice that if you look at this node here, this blue whatever, then the thing is that its left child has weight 3, its right child has weight 3, right? And so then you say to yourself, do I do any rebalancing because this looks really unbalanced? And the answer is no, because the weights are the same, right? The shape of these trees, it can't tell. It just says the weight here is 3, the weight here is 3, the weight here is going to be 7, right? And it cannot tell. It can't tell that these are different shapes. Okay, so now let's see what happens. So the weight of this tree is 7, the weight of this tree is 1, And I guess the weight of this tree would be then 8. 8. But the weight of this tree doesn't matter. So actually, I will delete the weight of this tree right now. The weight of this tree is 7. The weight of this tree is 1. And so now we have violated the rule. We have violated the rule at 31 because what we've done is we've detected that there is an imbalance. And 7, right? The rule is that one of the heights is bigger than 4. So 7 is bigger than or equal to 4. Yes. And also 7 is bigger than or equal to 1.5 times 1, which is equal to 1.5. So 7 is bigger than 1.5. Also yes. So that means rebalance. Okay. So we are rebalancing not here. So I should actually... here's the problem, right? Ugh. Where's the number? What happened to the number? Okay. Oh, that's what happened to the number. I'm kind of dumb. Let's see. Pull it up. Why won't it come to the top? Let's see. Control home. Okay. There. I know there's like a move to top. Move to layer. No. Raise? I guess we can also lower this one, maybe. Whatever. Maybe I'll just... Okay. I give up. I'm not going to color the node. Oh, and it made... oh, it made... That's why it was invisible. It made the actual... Okay. Wow. A yellow thing is invisible. Invisible on a yellow background. Okay, so I'm done. But anyway, so we're going to rebalance now, right? We're going to rebalance right here. So let's cut this subtree out. So the first thing I want to do is I'm going to copy the whole tree and then I'll just delete the other part. So here is the part that we need to rebalance. Here's where we are and here's what we're going to do, right? We're here. We're going to rebalance this. Let's get rid of the blue color. So we're going to rebalance. How do we do it? So if you remember, what I was saying is that you have to do something called an in-order traversal. And remember how to do an in-order traversal. An in-order traversal basically says, well, okay, here's what it says. It says go left, or maybe in order of node.left, and then it says read, print, whatever, copy the node dot value, and then here what we're going to do is then we'll do an in-order traversal on node dot right. And of course this is all pseudocode. They should actually be arrows and blah blah blah, but who cares? This is what the in-order traversal is going to do. Now, how do we know, right, the size of the array we need? Because we need to dynamically allocate this thing, but we need to know its size before we do that. And so in order to do that, what we're going to do is, what are we going to do? We're going to calculate the weight at the given node, right? You calculate, and so remember the weight of any node is equal to 1 plus, in this case it's the weight of the node dot left, plus the weight of the node dot right, which is in this case 1 plus 7 plus 1, right? And so this one is coming from the 31 node. This one is coming from this side. So what we need is we need an array of size 9, right? So let's build an array of size 9. And then we do an in-order traversal on this thing. So let's do this. So let's make a square and make it more square than that. There we go. Okay. No. Okay. So let's make, what is it? We need 9 of these. So 2. So this will be 8. We need 1 more. We need 9, like this. So what we're going to do, we know that all the stuff that's less, so now we have another question, right? To do this in-order traversal, we might actually, so there's a bunch of different ways to do it. I guess you actually could do something, you could do a pre-order traversal too, but I'm just saying we're going to do an in-order traversal because of this, and maybe you'll agree when I explain it. So the reason why I'm saying an in-order traversal is basically this. You can add an extra parameter to the in-order traversal, which may be some kind of index value, right? And so what I mean by that is that what you're going to have now in the in-order function is in order, and you're going to have the node and the index. And, well, okay, the node, an array, and the index. So the index will just be like some integer. The array will probably be like an int pointer, right? That'll just be a pointer to an array or something like that. And then here will be like the D node or whatever. But again, this is all, I really don't want to make this code. I want to make this more pseudocode, but I just wanted to add the types so you know what I'm talking about. So you'll have to, so in order to so here we'll do index, here we'll do index, and then here we'll do index, and I guess the other option, but you can't really do that on the right side. It's annoying, isn't it? Whenever you write something, then we'll have to do some kind of like index plus plus, right? So that's what I'm generally thinking, is that we're going to have to do something to the index, and then at the end we're going to actually have to like return the index. And so we're going to actually have to say like index is equal to this thing. Going to use the index, add 1 to the index, and then we'll do index equals, I guess it actually doesn't matter what it is. No, it does. I guess it does. It matters for the parents. So we'll have to do something with the index like that. I'm not 100% sure that this is exactly the solution or if it'll work, but we'll you know, I think it's pretty close. So let's do an example here. So basically here what we're going to do is a little in-order traversal. So remember, the in-order traversal is going to go left first, then it goes left again, left again, left again. And so basically here we're going to track the index. The index is going to start out at 0. And so what we're going to do is go left, 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 left. And finally when we hit the leftmost thing, we're going to say, okay, cool. We hit the leftmost thing, we write 21. We add 1 to the index, so now the index is 1, right? And then we return. So we'll return the 1. And then here it says, go left, but we already did that. And then it'll say, read this node. So now we'll get 22. And then we'll add 1 to the index and return it. Is there like an edit? Okay, I think the easiest way is just to delete it, type 2. And let me delete all these weights, because they might be confusing. So here's the index now. So this was index 2 that's going to get returned. So this is index 1. These are not weights, these are indices. Let me just write that. Numbers inside nodes are values. Numbers outside nodes are indices, or whatever. There we go, indices. Not weights. Not this time. And so then here what we're going to do is we're going to say, okay, 2 gets returned up to here. And then since there's no way to go left, this will get promoted to 3. Right? This gets promoted to 3. And then we type in 23 into this block. And then here, this gets promoted to 4. And then we type 24 into here. Like, actually doing an in-order traversal is pretty easy. Technically, if you have a vector, I guess you could always just do an append every time. But if you have an array that you know the indices, then, yeah, unfortunately, you're going to have to do something like this, where you actually keep track of it. Okay, cool. So then what you do is finally we have a write node. So we'll pass 4 down to here, right? So 4 is down here right now. And then 4 gets passed down to here, right? And so it goes to 0, 1, 2, 3, 4, index 4. So we'll write 25 into index 4. And then we promote this to 5 and return it. So then this is 5 now. And then what we're going to do is we pass 5 down to here. Oh, I'm sorry. No. We're doing in order. So then we just read this. So it's 27. 27. And then we promote it, right? Index plus plus. So we get 26. Or 6. Not 26. 6. And then we pass 6 down to here. It gets promoted to 7. Like this. And then 28 goes into here. All right? And then basically what you're going to do is you're going to pass this back up. So 7 gets passed back up from the recursive call, right? It gets passed back up to here, gets passed back up to here. So 7 gets returned here, and then 7 gets returned here. So then 7 gets passed up here. So we write 31 into index 7. And then index, and I guess then we promote it to 8. Or I guess actually, gets written into index. It gets written into index 7, and then the number gets promoted to 8. We push it down here. 45 gets written into index 8. You add 1 to index, it becomes 9, which is actually past the end of the array, but that's okay, because the total number of things that we've written is this. So now, we've done it. We've made our sorted list. So we've done our in-order traversal of this entire list. Oh my god, that was... Okay. But then what do? So now we forget about this tree structure. This tree structure is going away now. Now what we have to do is we have to make a new tree. Now here's the secret. To make a new and essentially perfectly balanced tree, and they do show it in the diagram, is you take the middle element, right? Middle element becomes the root. So 25 becomes your new root. Let's get a bubble. 25 becomes a root. And then what? Right? So once 25 becomes a root, then you have to recursively call the subtree structure, like create subtree on this and create subtree on this, right? And now, of course, we're in a different case. So in this case, it's nice because there's a middle element, right? Like the 9 divided by 2 is equal to 4, and 0, 1, 2, 3, 4. It gets us right to here. There's a single middle element. It divides the two things in half perfectly, etc. Here we're going to end up with something that isn't quite as perfect, but I think it's still okay because, well, it's not okay so much. It's just unavoidable. So if you divide this thing by 2, if you had, say, 5 divided by 2, or 4 divided by 2, you'll get 2. So unfortunately what ends up happening is 23 will become the left child, and who becomes the right child? I guess 31 becomes the right child, right? So that's what happens here. Whoops, what am I doing? Okay, so this is what happens. Let me make another copy. So this becomes, let me just save this because just in case it decides to make it delete itself. Okay. All right. So then what we have is we have this. So let me delete this box. Let me delete this box. We have 23 is the left child here. And then 31 is the right child. And then finally what we have to do is we have to call the thing recursively again on... And you see why this is actually not really the thing that... Like, if you're going to build a self-balancing tree, this is not the thing you do, because this takes... this is actually an O of n operation. And the reason why it's an O of n operation is because it has to basically traverse the subtree and another O of n for the reconstruction. And so, you know, O of n plus O of n is O of n total, which is bad. And the reason why it's bad is because if you think about it, it's not doing things perfectly, and also AVL gives you O of log n time, right? So for insert, delete, find, rebalance, etc. So AVL is way, way, way better in terms of time performance than Discord trees. Which is why Discord trees are not really a thing, because you wouldn't invent something that actually reduces the performance of a data structure like this. Okay, so now that we have this level, let's do another level. So I think that once you find 45 here, right, 45 we can just replace with a single bubble, because that's fine. The length here is 2, so I guess it would pick the 28 maybe. And this we can just replace with a bubble, because it's a single node, right? A single node is not, it's not the most, what should we say? Not the most thought-provoking case. It's just, you know, if you have a single thing in a box, you just put that box in a node, and you're good. So here, what we're going to do is we're going to say, okay, the size of this thing is 2. 2 divided by 2 is equal to 1. So you notice that if we had... The same thing would be true if we had size equals 3, right? And we do 3 integer divided by 2 is equal to 1, right? So int division. And so the point is that because 3 divided by 2 is equal to 1, what we're going to do is we would always pick... Like if you had 3 things, you'd be picking the middle element, right? That gets us to the middle element. Here, there's no real preference, because either we pick 21 or we pick 22. And as I say, there's no real preference. But if you do the calculation like this, if you just take the size divided by 2, then you're always going to end up with picking the kind of right element. So then what we're going to end up with here is we'll have 22 in a bubble. I guess, no, I don't want to draw a new one. I'll just copy paste. Here we go, 22 in a bubble. And then we'll have 21 in a box, right down here. And then here we'll do 28 in a bubble, and we'll move the 27 box down here. Okay. So this is the way to do this kind of structure. And then, of course, here for the last step, let's see. Okay, let me just copy paste this whole structure again, and we'll just do one final answer. I know that I could just do it there, but I'd like to keep each step separated. So even though it's pretty obvious what's going to happen now, I'd like to make it its own step. Okay. So this is how the Discord tree works, right? This is how it works. And then, of course, you might say, all right, cool, I have just done this entire restructuring operation. Now what? Well, remember how this thing was actually part of this tree over here. So what we're going to do now is we are going to copy-paste like this. And then we'll delete everything over here. Delete all of this crap. Like that. and then you stick this on right here. So actually we can't quite stick it on there because it's too big, but we can do this, and then it should be okay. So this is kind of how it works. And now, of course, you actually would have to compare this one, right? So actually, you have to do this recursively. So now that you're here, this makes it even worse, right? Even worse. We have to compare weights now again, right? So the weight here, what was the weight here? The weight here is 9. And the weight here is 4. And so if you know, the weight of both of them are bigger than 4, and the weight of 4 times 1.5 is 6. So I'm not going to redraw the whole thing, but you actually have to redo this entire reweighting operation, right? You have to redo it recursively, and you have to do it like this. So let's do it again, right? So what we're going to have to do is we'll have to take this whole tree, and we add on 5 elements. So let's take the old array. We'll add on 5 elements, like this, and like this. And so then what you're going to have to do is redo... oh, actually, no, they're added at the beginning because it's less. There we go. Do this. Drag, drop. What's this blue line? Delete. Thank you, Mr. Blue Line. Okay. So now we'll just do an in-order traversal here. 4, 7, 8, 12, 13, like this. And so then what you're going to do is, how long is this thing now? So this thing is now... let's think about this. How long is this now? It's 0, 1, 2. It's 5 plus 9, which is 14 things long, I think. Right? And so 14 divided by 2 is 7. So since 14 divided by 2 is 7, we get 0, 1, 2, 3, 4, 5, 6, 7. So now 23 becomes our root. Right? So 23 becomes our root. And then we get the subtree reconstruction. Here's one subtree reconstruction here that we're going to do recursively. Here's the other subtree reconstruction. And then what do? Do the same thing. What am I doing? This is 7 things, so 12 becomes the new root. Right, so let's do both reconstructions, even though you're going to do it recursively, so you're only going to do like one of them and then the other one when you get over there, but whatever. So we're just going to do it recursively at each level. So let's look at this. So this is how it works. So you'll take this one, give this one a circle, right? So when I change it to a circle, that means that you're putting it inside of a node, and you're reconnecting the node with its parents, and then you're calling like create left subtree, create right subtree, etc. And then you're going to have to do the same thing down here with 28. Oh, I'm sorry. I'm not, okay, so what is this? This is size 6, divided by 2 is size 3, so actually I was still right with 28. I thought that they were both equally sized. So there we are, delete this. And so now what we have is this operation here. And then we'll have to do it again recursively, so let's do it again recursively. So we'll pull out a 7 here. So 4 and 8 go down. 7 stays where it is, more or less. 13 and 22 go down. 21 comes back up, like that. 25 stays where it is. It's easier just to drag everything down and then move this back up. And then, whoops. And then we pick one of these. It's kind of random, except for the fact that if you do I'm kind of doing the stupid algorithm where you have 2 elements, you divide that by 2, so you get 1. So I'm always kind of, I think it's, am I left weighting the tree? Yeah, I'm always kind of left weighting the tree. If you do it the other way, you're going to right weight the tree slightly, but as you see, it actually doesn't matter because you have to make a choice, right? You have an even number of elements, you're subtracting out 1 to be the root or the subroot, so unfortunately you're going to have a division that's not equal on both sides. If you had an odd number of elements, then you'd have that extra element to make it into the root, and you just don't always have that. So that's what we got here. Here we are, and here we are. Right, that's that layer. And then finally, the last layer for the Discord tree is... So this is why I want you guys to make sure that you implement the Discord tree early, and that's why I think I'm just gonna count it as some kind of homework. I want to see all of your Discord tree implementations by the 23rd, and the reason why I want to see them is so that they are done by the 23rd. I guess, you know, I don't want it to add extra pressure for you for the project, but I definitely want to get this stuff, because the thing is, like, if you haven't done this, and then you also have to do an AVL tree, we're going to experience what we had last semester, which is just a huge number of people just don't finish. And that's not what I want. I bet there's a command that prevents it from snapping like that. Yeah, I mean, look, I'm willing to give as much feedback as you want, but I mean, I'm probably going to count it as some kind of completion grade. I'm not going to grade it like it's a project. I'm not going to be running 100,000 test cases on it to just make sure it's like 100% foolproof. But I will be grading it on essentially completion, like how much you've done on this thing, because I don't want the problem is if you let this go until the week, even if you just start on this the week before the due date, it's going to be very hard, right? And here's the reason why this algorithm is actually going to be harder than it looks, is that you're going to have to keep track. So I think what you're going to end up doing, at least here's my thinking. Okay, maybe I'm wrong, maybe you can think of a better way. So here's my thinking, right? And so that means, you know, take it with a grain of salt. But here's what I think. I think that I would keep it as an individual array, a single array. And I pass the array. So when I have like a construct subtree, right, like a reconstruct subtree helper function that is going to take an int pointer to an array, and it's going to have to take maybe like a start and an end, right? And based on that start and the end, you'll know where you are. So for instance here, this would be, and of course it's also going to have to take, and it should probably return like a node pointer so that we can relink. So in the end, what you're going to end up doing is you're going to end up saying something like node.left is equal to reconstruct subtree, and then you'll do something like array start and divided by 2, something like that. And then here you're going to do node.right is going to be reconstruct subtree array start. Or it's going to be like what? It's going to be start plus like end minus start over 2 or something like that up to end, something like that. Don't take again, don't take that as gospel, because that may or may not be correct. And then so when you reconstruct, and so what you're noticing is going to happen here is like here is index 0 and here is index whatever this is, like 14 or something. I guess this would be index 13. So here the start thing you're going to have to pass is 0, and then you get 1 2 3 4 5 6 7. So you'll pass index 7 here, and then this will be index 8 will be start, right? So you'll get start, which is 0, plus end minus start over 2, so 14. It might even have to be like end plus 1 minus start over 2, something like that. I don't know, something like that. You might have to do a plus or minus 1 correction factor to get it right. So we'll have to do like 14 divided by 2 plus 1 or something like that, or I don't know. So I can't promise you this, but it's some kind of weird offset like this, because it's halfway through, but it's the next one, all the way up to the end, which is 13 again, right? And so then here you're going to have to pass index 0, and here's index 2, right? And then here you're going to have to pass index 3 as the start, index 5 as the end, index... And I think you might even have to add another 1. So you need the end plus 1 is because the size is 1 more than the last index, right? So for arrays, they go up to the size minus 1, so that's why I'm adding n plus 1. And then the last plus 1 is because we are skipping the node that we just created, right? So that's kind of my thinking here, is that you'll need an n plus 1 because in here. So this n plus 1 is because, right, this thing is true because the size is always 1 more than the index. So that's size minus start over 2, really. And then what we're doing here is we're saying plus 1 because we want to skip. You notice here that here we have to do, we have to skip 1. So, oh, I'm sorry, this shouldn't actually be 3. This should be 4 up to 6. You see, I didn't skip 1. That was very bad, right? So we never see the index 3 again because index 3 went into creating this node, and index what? 8, 9, 10, 11 went into creating this node. So this is index 12, index 13. This is index 8, 9, and 10. And then finally here, you can basically tell that you're at the bottom because the index, hopefully the start is equal to the end, so the start index will be 0, the end index will also be 0. Here the start index is 2, the end index is 2. Here the start index is 4, the end, etc. 6 and 6 and 8 and 8 and 10 and 10, right? And then here you'll get 12 and 12, right? So you can tell that you're at the end when the start index, so that's how you end the recursion, right? By testing, basically, if like the start is equal to the end, then what you do, right, then you create, what do you create? Create the new node, return it, done, right? That's all you have to do. That's like your end recursion case. That's, I guess that we call it the base case of the recursion, right? So that's kind of the point here, is that you're going to have to do something like that. So that's Discord trees. I hope that this made some sense. I think I did an okay job here explaining it kind of. So the whole point is that this is a fictional data structure, right? But now you know how to implement it. You know, I give myself a B+. So I haven't actually implemented this thing, but I promise you that you will spend, if you implement it at least in the way that I'm doing it, you will spend a huge amount of your time pulling your hair out just on the index stuff. I don't 100% know if there's a better way to do it, though. Like, that's, you know, I can say that that's going to be the hardest part. I don't necessarily know there's a way around it. I think, you know, what have we learned? We've learned how to insert and rebalance and even remove from these structures, right? So remember, removal is literally you just find the node and you just replace it with vacant, right? So it keeps its value, but then you set the vacant to true, right? So that's how you remove. Now, the only question I have, which is I think it's a good question that maybe people will ask or think about, is if you're restructuring and you come across a vacant, you don't take it, do you? Right, when you're doing your traversal. So let's see here if there's anything. So this function, the node parameter refers to the root of the subtree, it recommended blah, blah, blah. Create and manage the dynamically allocated array used in your helper functions. No vacant nodes should be balanced, so the array should size should reflect that. So vacant nodes in node subtree must also be deleted during this process. Yep, so vacant nodes outside of the node subtree will not be deleted. Right, so basically, if you start rebalancing, so that's a good thing to say, is that if we started rebalancing this thing, and instead of having, say, 21 in here, you had 21 in here, but vacant was equal to true, then the point is that this would probably not end up in the final data structure, right? Unfortunately, the rebalancing of the whole data structure would change. I think like 22 would go up to be the root, and you'd have some different balancing operations that happen. Unfortunately, because it'd be nice if I could just say like, oh, if we delete this node, then like this would happen. But it'd just be like this, but it really wouldn't, because notice that what happens is your position in the array can be very close. For instance, here where 22 is close to 24, but look at what happens. 22 is all the way down here. 24 is all the way down here. And so it does not mean that you're like siblings or close in the tree, right? You are close in value, that's true, but you're not necessarily close like graphically or geometrically or whatever you want to call this. Distance, like your distance here would be like 1, 2, 3, 4, 5, 6. So even though you're only 2 away numerically, you're actually distance 6 away from each other on the tree. So that's a problem. So yeah, okay, so I think the last thing to say is whenever you rebalance, so instead of rebalancing just on the nodes themselves, what you want to do is if you come across a vacant, right? If vacant, what you do is you don't take the node value and you don't increment the index value either, right? And you build an array, so your array has to be equal to like a new int of size, something like weight of the node minus vacant of the node, right? Because you're not going to include any of the vacants. So I was just doing it with the weight because I didn't have any vacants in the example. But if you do that, then the thing is that you have to do weight of node minus vacant of node. So you'll have to think about that too. In terms of AVL trees, I didn't say another word about them. So we'll continue talking about... So this lecture was actually not really about anything other than the project, because this is just Discord tree stuff. It's cool to talk about. Basically, what this gave us is it's a perfect... What it's normally is like, normally this is 5 minutes of me saying, we don't weight balance because A, it's complex, B, it doesn't give you the trees that you expect, and C, it takes O of n time sometimes, which is slower than the trinode rotations of the AVL, red-black, splay, etc. So the reason why the rotations that I described in the previous lecture are the things that exist, right? They're the things that happen, is not because they are like ordained by any, by the gods. The reason why they happen is because they give us a way to do an O of 1 operation. So each rotation themselves is an O of 1 operation per rotation. Whereas here, actually we have it. So each rebalancing takes O of n time. If you have to do multiple rebalances, say the height of the tree is about log n times O of n rebalances. That's an O of n log n for a single insert rebalance in a weighted tree, right? So a single insert weight rebalance in a weighted tree basically can result in the entire reconstruction of the tree. In fact, it can multiple times, right? This is extremely bad, right? It breaks the whole, and all the advantages that you have from a tree structure, weight balancing breaks those. And so, if your question is, why don't these things exist in nature, right? Why don't weight balanced tree structures exist in the sense that, like they're used professionally, they're used out in the research community, blah, blah, blah. I mean, I'm sure that there are some that can be fixed a little bit, but the thing is you're always trying to fix the inherent deficits that the weight balancing gives you. Height balancing gives you good information. Weight balancing gives you kind of bad information. And so you can always just try to make your best of it. And that's why none of this stuff is like official. You know, you're never going to see this in a 341 textbook. No data structures textbook is going to talk about this because weight balancing is just so slow compared to height balancing using the tri-node rotations that it's really suboptimal. Now, of course, this is a project, so we don't care. We're just making you do this for, you know, for our own amusement. But anyway, so this is usually the talk that I give about weight balance stuff, and I don't actually go through the construction of a weight balance tree like this. Okay. So I think in terms of exam prep, since I will release the exam, but I'll probably do some exam review on Thursday, maybe right before I release the exam or something like that. And so what I'm going to do is I will give you right now, I'll just post them on the Discord. I will post you 2 previous exams on Discord, and then I'll send them out by Blackboard sometime today. Okay? And you can look at them. Let me just say that the fall 2021, let's see, go up to question 7. Don't go past question 7. So for the fall 2020 exam, and I'll write this on the stuff, fall 2020, go up to, but no further than question 7. And the reason is that the material from question 8 and 10 to 10 will be exam 2 material. I delayed the exam 1 last semester, and the reason why I delayed the exam 1 last semester was because of last semester's project 2. And I'm not going to delay the exam this time because I think the timing does work out better. If we get the exam over with sooner than later, it'll be less painful. So there's less material on it. So there's some questions that you should be like, I don't understand those questions. If those questions are 8 to 10, that's okay. Okay, so I'll release the exam. I think that's it. Have a good day, everyone.